Okay, guys, for this one we're going to be talking about lesson 4-4, which is graphing polynomial functions. The things that we are going to focus on in our graphs of polynomial functions are the degree, the end behavior, and then the leading coefficients as well. And we'll kind of talk about each of those. And we'll kind of talk about what the degree has to do with the shape, how the leading coefficient can affect the orientation of whatever graph we have, and then end behavior to help basically describe what's going on. So let's start with the degree first. So the thing we need to know is what is a degree of a polynomial. So whenever we have a polynomial, that means we have at least a term. Typically, when we have a polynomial, we have multiple terms strung together through addition or subtraction. So, for example, I could have, usually it's going to be represented as a function. So instead of y, I would have f of x, means pretty much the same thing for us, equals, and then let's use a trinomial for this one. So this is just going to be an example. Just kind of pulling off numbers here. And let's have 3x squared minus 5x plus 10. So the first thing we mentioned was a degree. So a degree is just our word for whatever the largest exponent is in the polynomial. So in this case, the 10 would have an x that is raised to the power of 0 because we're not even showing one there. This has an x to the power of 1. This has an x to the power of 2. So that 2 is the largest exponent, meaning the degree of this entire polynomial is 2. That's going to affect what shape we end up with. So the biggest exponent is going to affect our shape. If I had tacked on a x to the third power at the end, the degree would change. The shape of the graph would change to the degree of 3. So let's talk about what degrees make what shapes. So let's erase here. Okay, so we'll talk about the first couple, and then it kind of starts to form a pattern. So the first one would be a degree of 0, meaning we don't have a variable at all, meaning it's just a constant. So we would have, for example, y equals, or f of x equals a constant number, which means our graph is just going to be a straight line. Something like that. So that's if you have a degree of 0, we're going to completely horizontal line. All right, next. If we had something that had a degree of 1, meaning just an x with no exponent shown, well, that's just like our slope-intercept form that we've dealt with in the past. Basically, we're going to get a straight line. So if that's, oh, that's a really bad coordinate plane. It's a little bit better. So if that's our coordinate plane, we might end up with a straight line just like that. So that's if I have a degree of 1, where the biggest exponent that we have in the polynomial is a 1. After that, so we'll go, like I said, through a couple. If I have a degree of 2, so an x squared, kind of like the first example I showed you, that's going to lead us into a quadratic function, meaning I'm going to have a parabola shape, maybe something like this, that U shape. Okay. After that, we're going to have something to the degree of 3, which means it is cubic. With a cubic, it's going to start down and up. With a degree of 4, I'll put these kind of on the screen at once here. Degree of 4, I believe, is called a quartic function. We wouldn't usually use that term in my class, but something like this, like a W shape. So this is degree of 3, 4. Let's show 5, and then we'll kind of talk about what we have here. Degree of 5. We'd have some waves in there. Something like this. That's 5. Okay, so kind of messy, but we'll talk about what that means. You probably notice that we got more of these maxes and mins dependent on the higher degree. So if I had a degree of like 100, I'd be bouncing up and down a whole lot, versus something with a degree of 0 is completely flat. You may have also realized that for our odd degrees, so 1 and 3 and 5, the arrows at the end ended up pointing away from each other. So they finished kind of opposite directions, whereas something like 2 and 4 either both pointed up or both pointed down at the end, something like that. So that's going to help us think about our shape and our end behavior is what we're going to call it. Basically what's going on at these arrows. And then the leading coefficient's basically going to help us see if our whole thing is reflected or not. So with a positive leading coefficient on a odd degree graph, so like 3 or 5, it starts down and ends up. Whereas if it got flipped, it'd start up and end down, basically the opposite of what I have here with 3 and 5. For something like 2 or 4, if it's positive, they're both going to be pointing up, whereas if the first coefficient, the leading coefficient, is negative, they'd both be pointing down. I believe the example I gave for the degree of 2 actually was pointing down, so it must have had a leading coefficient that was negative. Okay, now that we threw a bunch of this at you, let's kind of see it in action. Let's take a look at this IXL that I have pulled up, and we can talk about a few things that help us make some decisions here. So it says match each polynomial function to its graph. This is IXL L14. So we have kind of limited options here, especially for the first ones. It's just 2 and 2. It'll eventually get a little bit more complex. So let's take a look at what we have here. We have 2 polynomials that are degree of 2, because that's the biggest exponent that appears for each of them, meaning both of our graphs should look like quadratics or parabolas. They both do. Good. Because they're both even degrees, both of their arrows should be pointing either both up or both down, depending on if it is positive or negative. They both do that. We're good there. How I might represent that, not that it asks for it in this one, but in the future, let's look at this one. We have our x-axis and our y-axis. So if we wanted to label these in terms of the biggest numbers you would see on those axes, or on these axes, they would keep going to infinity. So positive infinity would happen up here for y and off to the right for x. And then we would get negative infinity at the bottom for y and to the left for x. So what we could say is as the graph travels towards negative infinity in the x direction, so basically as it goes left, it would travel towards positive infinity in the y direction. So what we're stringing together there is as the graph goes left, it goes up. And how we would say the other way would be as it goes right, it goes up. Basically, as it goes towards infinity in the x direction, it also goes towards infinity in the y direction. Like I said, that's basically fancy for when it goes to the right, it goes up. Or a previous one was when it goes to the left, it goes up. This would be as it goes to the left, it goes down. As it goes to the right, it goes down. Okay, finally, to help us make our choice here, we look at the leading coefficient. So what's out in front of the thing with the biggest exponent. So in this case, it's a 1. This one would be a negative 1. We said when it's positive, both of our arrows in a even degree like this, like 2, point up. So this one, because it's positive 1, must go with the one that has arrows pointing up. A negative must go with the arrows pointing down. Awesome. Okay, let's jump ahead a little bit. Let's see what changes we see. Okay, something like this is pretty similar. We have x to the 4th, another even degree, so they must have arrows pointing the same direction, both up and both down. They're both to the 4th power, so the shape's going to be pretty similar. This one is positive, that one's negative, so positive goes up, negative goes down. That's how we're deciding here. Okay, a couple things to talk about here. I think if you understand the shapes, it's probably pretty easy at this point. A squared degree or a degree of 2, especially with a positive leading coefficient, would make a parabola that opens up. It must be this one. This has a negative on it. Fourth power must be this one. This part over here, just so we see it, that helps us determine our roots. So basically where we cross the x-axis or x-intercepts. We would need to think about what would make each of these sets of parentheses equal to 0. So in this one, it would be a -5, because -5 plus 5 is 0. If I zoom in on this graph at the x value of -5, that is an x-intercept. So that's what that's telling us. This one would be -4. The other would be -3. -4 is an x-intercept. It crosses here. -3, notice it doesn't cross, but it hits it and turns around. That's what this squared root is doing. That's basically like I have x plus 3 twice, meaning it's going to go up to -3 and then immediately bump back down. So just something to help us kind of wrap up that. So I'm mostly going to say, as long as we're okay with the in behavior, leading coefficient, and degree, what those mean, that's going to be good for us. And then we may approach this specific IXL a little bit later on. All right, if this helped, feel free to leave a like and subscribe if you haven't yet. We'll see you.